Sure. Very good morning, good afternoon, good evening, team. Myself, Prasanna. Let me share my screen and just confirm whether you are all able to see the screen and details. So I have been in the industry for the last 2 decades, and currently I'm based out of Saudi Riyadh, KSA. I head a lab here, part of our partner ecosystem. I work for a company called HCL here, and I'm sure it is the same HCL that you see in India, uh, where we work on some of the advanced technology in terms of AI, machine learning, and IoT, and cloud. That is the focus here. In today's session, I hope my voice is clear and all are able to hear me okay, please.
Yes, all good so far.
Okay, wonderful. Um, so this, I have quite a lot of content as part of session. The way in which I wanted to structure the today's session, as I discussed with the Vivek and Vishal team, is basically probably we can have multi-part sessions for the quantum machine learning as such. On today's session, we will probably give you an introduction and the basic premises about it. And there are when you look at quantum machine learning, I'm sure if you had already an introduction, there are two ways that you can actually get started with this. One is from the mathematical background towards it, how you approach the quantum machine learning part of it. The other approach is towards programming part of it. And what I would like to touch predominantly on the programming part of it, because majority of the technology people would be more interested on that way of looking at the quantum machine learning. So that is what the today's focus is. Because once you learn this and the mathematics behind it, you can actually understand it as similar to how you apply your machine learning concept. So you can directly start utilizing your logistic regression and linear regression models, but you can learn how the neural network works at the later point in time. So the main focus of the programmers would be on how do I use these technology for my problem statement. So that is a focus area. Okay, and so let me start. So we all are aware, and I'm sure all of us have some background in terms of what is bits. A typical classical computers that we use all work with the basic premise of bits. The basic premise of bits comes down to a very simple construct called zeros and ones. So at any point in time, a bit can have a one or other state. Either it can be a low charge state or a high charge state. That is how, even though you are talking about all the different application, at the end of the day, machines that you're interacting with, your laptops and desktops, predominantly understand only bits at the end. So before I introduce the quantum computing, I wanted to take an opportunity just to explain the concept so that you will understand what is going on behind the screen. Okay, we all are aware about coin toss example. Assuming I'm going to give you an example now. Assuming that you have a coin on your hand and you're going to toss that particular coin. So when the coin is on the hand, what would be the state of that particular coin? Anybody? What would be the actual details that you see in the coin? I want this to be an interactive one so that you can understand it better, the concepts. Anybody would like to say, you have a coin that you have tossed. Before you toss the coin, you had the coin on your hand. I'm sure you can very well tell, okay, the coin that I'm holding in my hand, either it is showing me a head or tail. You can relate this to a detail in terms of a classical computer. So at any point in time, the coin on your hand represents a state of a bit. Okay. Assuming that you toss your coin, the coin is spinning and it is in the air. So now if I ask you, what is the state of that particular coin, whether it is a head or tail, what would be the answer? I would like to understand from you guys. What would be the answer for this? I have tossed my coin. The coin is in the air spinning. What is the current state of that particular coin? Anybody? Am I audible? Hello?
Yes, sir.
Yes, audible.
Okay. Sure. Okay. So from all those who with the mathematic background will tell that, it is a probability. It can be head, it can be tail as well. And it can be head or tail. It depends on what probability that we think. We are talking about not the probability after you received the coin down on your hand or before you start tossing. The probability that I'm talking about is when that particular coin is in the air spinning, what is the value of it? Okay. So now if you read the value of the coin at the air when it is spinning, the possibilities are that at the same time, the coin can represent both head as well as tail. And that is the basic premise of quantum computers. Now here, when the coins are kept on a stable state, you will really know that this coin, what is the current state that represent a bit, where when the coin is tossed in the air and it might have head or it might have tail, or you can say it has both the states at the same time. So that is a different type of representation. That is what is called qubits. So we're going to, the whole quantum computing were based on the premise of qubits. Now, what are the actual differences? The classical computer, at any point in time, the basic value of the bit can be only one. Either it is in on state or off state. You represent them with ones or zeros. But in the case of quantum computers, that is, you are in the coin tossed state. Because the coin is in the tossed state, the representation of the quantum computers, the qubit, will be considered as a superposition state. Okay. What is the superposition state? The superposition state represent the qubit can have simultaneously the same value or both the values of zeros and ones. That is what the interesting characteristics of qubits. Okay. I hope you are getting that detail, what I'm trying to say. Assuming that you have, instead of 4 bits, you have 4 qubits. And in a typical, classical computers, if you have 4 bits, the amount of processing that is required to process some, say, integer value, you typically represent either 0001, that is one state, and 0011, 0111, or 111, or you can have multiple permutation combination of values. That is a typical classical computer. But assuming all the 4 qubits are going to represent both 0 and 1 at the same time, and typically you will be able to get all the calculations that you wanted to done with multiple combination of values at the same time. You don't need multiple steps similar to a classical computers to actually achieve what you wanted to achieve. So in this case, all the 4 qubits are going to represent zeros and ones at the same time. So if you consider, say, you want to do some mathematical calculation using this 4 bits, then all the different calculations with multiple different combinations. You want to take 0001, 0010, 0111, or multiple combination of this can be done at the same point in time. That is the basic difference between a quantum bit and a typical bit. And now, how do we represent, how do we see this quantum computers? This is one of the sample quantum computers that were built by various different providers, but this is one of the quantum computers image. And this you can assume that how computers were envisioned in 60s and 70s of the last decade. And we are in the very initial stage of quantum computers, where we are envisaging the quantum computers. These are the multiple different things that is required for building a single quantum computers. And let's look at who are all the different players who are in the whole space of a quantum computers. I've taken only a specific set of players here, and the typical technology players that we are interested on. And we can see that IBM, Google, D-Wave are three major players, and Microsoft is catching up, and there are so many other people who are also doing parallelly on this. D-Wave has been the predominantly the the early mover in the quantum computing space. Majority of the initial quantum computers that were developed by Google were all based on D-Wave technology. And IBM has their own quantum computing division. They predominantly focus on building from the machinery, that is the quantum computers, till the software stack that we talk about towards the end. Okay. So these are some of the players. So the chipset, let's look at. So Google initially released their Bristlecone quantum computer chip, which is just 72 qubit quantum computers. Imagine that it is somewhat you are saying we are going to create a computer, classical computer, just with a 72 bit. Now we are all talking about terabyte, TB's, amount of storage. So where currently the quantum computer space is. And the main purpose of Google creating this Bristlecone is predominantly used for their algorithm development and so on and so forth. And after Bristlecone, they have created something called Sycamore chip, and this was around 2-3 years back. And the Sycamore, the actual quantum supremacy that was released in last year by Google was done using the Google Sycamore chip. So to sink in on the perspective and the amount of time that is required to complete a specific process that can be done in a Sycamore chip in 3 minutes 20 seconds, and the same processing cannot be done on the latest supercomputer that you have currently. Cannot be done in the latest supercomputer. Just think in that for a moment. So that is the basic difference that we see. And IBM has also been working on their own set of chip. Hummingbird is their own quantum chip. In June 2022, that is very recently, IBM released a 1386 qubit processor, Kookaburra, and they already announced that they are already working on 4158 qubit chip that they are planning to release in 2025. So this is from the manufacturing perspective. Okay, the chips ecosystem perspective. Right. So just to reiterate, the normal computer, everything is done in a very linear way. You take some details and you put some processing and you get an output. But in the quantum computer, everything is done parallelly. Because the basic premise of the quantum computers were qubits, because the qubit at the same time can represent both zeros and one. And all that example that I was talking about, the 4 qubits that I was talking about, all of them can have at the same time, 4 qubits can have at the same time, and whatever processing that you wanted to do, and you can get the outcome at the same time. So if I say working on an algorithm which is trying to convert this particular string and do some processing to come out with this particular output, and you can apply the same thing, same algorithm at a quantum computer, where you can process all the different combination of values so that you can get the final outcome at the same time in a single pass. That's a basic difference. Okay, let's look at some of the basic differences. We talked about the qubits, and the power requirement for a quantum computer increases exponentially as the number of qubits are increasing, but it is somewhat linear in terms of normal computers. The other important problem the quantum computer face is the machine that I showed you. It has to be kept in a sub-zero temperature that is around minus 236 degrees Celsius. That is a typical temperature with which you may have to keep the quantum computers. Then only you will be able to experience the actual qubit executions there. And because the qubit executions are highly error prone because of the kind of temperature that you are maintaining, there is a lot of error that happens in the quantum computer space because we are at the very, very initial stage of working with the quantum computing space. But in the case of classical computer, the error rates are very, very negligible. So the quantum computers are well suited for optimization problems, data analysis and simulation. That is exactly where AI comes in. Yeah, predominantly the purpose of all our AI algorithms were optimization problems, data analysis, and simulations. So that is exactly what AI is craving for. But typical computers, we all have been using this. So that is a basic difference between classical and the quantum computers. Let's look at the programming perspective. So who are all the different players in the market, and what kind of a language and the frameworks, tooling ecosystem that is available, so that you can start programming on the quantum computers from today. So in if you look at, there are so many players, and among them the 3 players stand out. One is IBM, who though they have a full stack, and Google and Microsoft, where are the 3 players, top players, having a full stack of the details for your quantum machine learning processing. Okay, so similar to your typical classical computers, you need hardware. The quantum device that we are talking about, it is like your computer where the algorithms that you create gets executed, and you have an assembly language for the specific providers. We will touch upon this assembly language shortly, but effectively there are different assembly languages are being used. OpenQuasim and other quantum machine learning algorithms were used from Google and Microsoft. And there is an interesting thing called quantum circuits. We will cover in deep about quantum circuits. We will see some examples how we create that as well in the code examples. IBM has some framework called Qiskit, and Google has a framework called Cirq. And these languages enable you, these frameworks enable you all the different things that you wanted to do in the quantum computing space. In the sense, the way in which they are taking both IBM and Google, they are predominantly on the forefront in terms of quantum computer space, and they provide you a language or a framework that enables you to write your language in a typical programming language that you use, and they take care of converting whatever that you're writing into the quantum device understandable format in the backend. So from the programming language perspective, The three things: Qiskit, Circ, and the Quantum Development Kit from Microsoft were predominantly famous. Okay. So now, you're you could ask that, you're telling the quantum devices requires some 230 degree minus 230 degrees Celsius. How can I test on all these devices? The beauty of all these programming languages that these guys have created, they also provide a cloud-based access to this quantum devices from your home. We're going to see how that also happens. And those who have worked on mobile application development, they also can appreciate the fact that you do not really need a mobile device to develop your applications. The mobile application providers provide something called the simulators and emulators, and these emulator can help you develop your end-to-end mobile application on your PC itself. And once you are ready and the complete things are ready, and then you can go for deploying and testing it on your real device. And these quantum players also taken the similar approach, where they provide the frameworks to help you develop whatever that you wanted to develop on your local machine. And once you are ready, they provide a lot of simulators and emulators through which you can actually experiment the details that you have created. And once you are done, you can take that to the quantum devices for the final execution. It is a similar approach being followed there. Right. So let's, before I get in, let's look at what is the approach that is being followed in terms of a typical classical computers when it comes to the programming execution perspective. So I'm sure majority of you might be a programmer, and you write your code in some of the language. It will be typical English, but specific to some construct that has been put forth by, say, Python, say by C# or whatever the language that you're talking about. So once you write the language, and there is something called compilers, and the compilers will take care of taking your source code to the machine code, and the machine code is what gets executed at the end of the day on your machine, and you get the output, just to simplify the whole process. Okay, but the difference here when it comes to quantum computers, because you can think of quantum computers are like 80s and 90s of classical computers at this stage. I'm sure those who have worked in 80s and 90s on the classical computers, you may have to write your program on probably a card, and that card you have to insert into your computer. The computer basically process it and comes back with the output. Okay, that is a very early stage of your development. And similarly, there are assembly languages were there, and using that assembly language, you could be writing your program and get that deployed on the devices for getting the details. Okay. So now in the case of quantum computers, the programming flow happens like this. Okay. So assuming you first define what is the problem that you wanted to solve, you define the problem, and you write the algorithm to actually solve the problem. This is a typical English way of representing. Okay. So till now, we do not have the approach of directly taking our quantum algorithm to the quantum computer. We are yet evolving. There is an intermittent step that has been introduced, something called quantum circuits, meaning before you take your algorithm to the compilers, you need to convert your algorithm to something called a quantum circuits. And these quantum circuits will get sent to the quantum compilers, and the quantum compilers in turn can utilize a quantum simulator or can utilize the real quantum device or the chips for your execution. I hope it is clear. So we are introducing the difference that you see is between a typical programming flow of a classical computers and the quantum computers are the algorithm has to be converted to a quantum circuits, and from the quantum circuit you take it for your compilers and your implementations as such. Okay, that is a basic premise, basic difference. Okay, so this is the evolution of your classical computer to a quantum computers. Okay, uh, so you in the 1950s you typically return your language in an assembly language, and that gets converted to relay circuits, and that gets executed. So we are around the same type on a quantum space. Okay, and in the class, once the classical computers were introduced, you write your algorithm, and these are the high level languages, and the compilers basically take them, and based on the classical architecture, it will convert the details to the internal gates and bits and so on and so forth, and that gets executed on a VLSI circuits, and the semiconductors, transistors basically execute the things at the end. So what is the evolution that we are seeing is we're going to use a similar construct, but in the coming days, we may be using your algorithm. It will be in the typical high level languages, and you will have two compilers part of your system. One is classical compilers, another one is quantum compilers. This is what we see happening in the future. So you choose, like, you go and execute your your algorithm on a classical architecture, or you wanted to execute in a quantum architecture. The other approach to think about it is a hybrid approach. For example, even now the structure or the way in which your quantum computing languages are evolving, what we see is part of your machine learning workflow, you may have to require your EDA process to be done at the beginning of your processing, and the EDA process can be done with a classical computer. Once the EDA process is done, you may have to apply some neural networks there. So the neural network execution can be done in a quantum computer instead of using a classical computers. And once that execution completed, and let's say your weight adjustment has to be done, so you take that output of a quantum computers and do an adjustment on your weight, and probably retrain your whole models and so on and so forth. So this is going to be a combination of your classical and the quantum computers. That is what we see in the going forward. Okay, so guys, I see very quiet thing. It is not much interactive. So just stop me in case if you are not clear or anything. I'd be happy to answer any questions there. Okay. Okay, so we're talking about this circuits. What is the circuit? This is an example circuit that you see on your screen, where um, this utilizes something called gates, and we will see in deep about how do we create all these things with practical shortly. Just to give you a funda about how the circuit is going to look like. Okay, the circuit that you are seeing is what is used for random number generator. So in a typical programming language, you put, say, random of some a range that you give, it automatically generates it. But here we are saying it's a 4-qubit based random number generator, or 5-qubit based random number generator, and you utilize some gates and operations for getting the final output. Okay, we will see more details about it. Don't worry about it. Okay, so okay, you are telling the quantum computers are very requires a typical high like temperature management and all has to be done. How do we actually interact with it? The typical process is you utilize your classical computers, your laptops and PCs for interacting with it. Meaning, whenever you wanted to do something, you basically take your data and everything that is there, and on the classical computer, send it to a quantum computer, and that process it. And once that processing is done, you get back the final outcome and look at that number and or the outcome on your classical computers. That is the interaction with the quantum computer. This is the approach that is being followed. Okay, so what we need to do, or how the quantum and the classical computer interacts with each other. So you have a problem that you wanted to solve. It could be a salesman problem, or you wanted to optimize your machine learning algorithms, so on and so forth. What you do is in the classical computers, you define your algorithm, and on any high-level programming language, you need to in the classical computer convert them into an algorithm to a circuit. So these circuits are the one sent to your quantum computers. So the quantum computer receive this detail, and they process these details on the quantum computers. And once the computation is done, you read the response from the quantum computers and display that details in the classical computer so that you can process it. Okay, right. Let's start looking at how do we do all that we understood. We introduced different frameworks, and I'm going to introduce you to a framework that is being developed by Google called Circ. The Circ is an open source programming language for your quantum algorithm creation and the circuit creation. And you can refer this link, which is a GitHub link for you can even contribute part of your Circ development and so on and so forth. And the interesting part is it's all developed using Python for you to write, manipulate, and optimize your quantum circuit, and running them against quantum computers or a simulator. Okay. What it enables, you can create qubits, you can create gates, operations, circuits, moments, apply it on the simulators or on the real device for the execution. So this is what our today's focus. So in today's session, we will be looking at how do you create all this practically on using Google Circ as the programming language. Okay, right. So before we get into that, let me just try to introduce some of the basics. This will help you understand how do you interact with circuits, how do we create, what is gates, and so on and so forth. Okay. So the first is qubit. We introduced you what is qubit. How do we represent the qubit? What is it actually? Okay. The state of the physical system in the quantum mechanics is represented by a vector belongs to a complex vector space. And these physical state of the quantum system is represented by something called a Ket notation. Okay. So as soon as you read this statement, you can say, Prasanna, I lost you. So don't worry about it. Just be with me. I'll tell you what it is in a minute. Okay. So we are talking about bits and qubits. Bit has a state of 0 and 1. And you need to represent qubits. And how do we represent qubit? You will utilize a notation called Ket for representing the qubit. Okay. So this is called 0 Ket and this is called 1 Ket. And because the bits are having only one state, bit either can have 0 or either can have 1. But the qubit can have both 0 and 1. And to represent differentiate the state of the qubit, we represent them using a vector space or vector representation. Okay. So there are two words. One is vectored and the vector space. What is this vector space and what is the vector that I'm talking about? So this is the representation of your grounded state, and this is the representation of an excited state. What is this grounded and the excited state? Let me cover that. Okay. So we told this is the Ket notation that represents. Assuming that in a classical bit, the bit can be in 0 or 1. How does it know? Because the state, this is a ground state, and this is the excited state in a classical computer. At any point in time, the classical bit can be either in a ground state or a excited state. But in the case of qubit, we're going to take this whole space as the vector space. This whole sphere that you are seeing as the vector space. And this vector space is going to have multiple locations. And each and every location is going to have a different representation of that location. I hope all of you agree. And within this vector space, the bottom of this is going to be represented as ground state, and there is an excited state. You do it at the bottom or top, it doesn't matter, but effectively what you say is, in this whole sphere of space, my qubit can be in a ground state or excited state or any state in between this. So that is what is represented by the ket notation here. Okay, so if it is in the ground state, that is represented by a vector called 1 0. If it is in the up state, that is excited state, represented by this excited state. Okay, let me take you to the next level of understanding. Okay, so this is what we saw. This is an excited state. This is the ground state. Assuming my qubit is here in this space, so I need to calculate what would be the value of my qubit at this space, at this particular state. It is an intermediary state, and this intermediary state is going to be represented by this, and this will have an influence of my ground state as well as the influence of my excited state. So that is what is represented by the formula here. The state of a qubit is represented by this, and it has the probability of 0 state and the 0 qubit, 0 ket, and the probability of 1 state and the 1 ket. Hope I'm making sense. Okay, so that is what it represents. So rest of the math, we don't bother about it. Let's, if you understand this, that is enough. Okay, at this point in time, right? So the first concept we understood, how do we represent them qubit, which is a ket based representation. The next important thing is a quantum entanglement. What is this quantum entanglement? To definition wise, if two qubits are in a quantum entanglement, then if you absorb a value of one qubit, you will be able to get the value of other qubit automatically. An example here, let's say you have a gloves. The gloves will have two pairs, one for your left hand, one for your right hand. And let's say you kept these gloves in a closed box, and you want to take out one gloves from that. And when you put your hand and you're taking out a gloves, when you are taking out a gloves, if you get your gloves, right hand gloves, then you already know that I have already got my right hand gloves. So the other gloves that is inside the box is nothing but a left hand gloves. You already know the value of it. This is to simplify the quantum entanglement. You have two qubits that you consider them as an entangled one. So if you can read the value of one qubit, you already know what is the value of other qubit. That is what quantum entanglement, just to simplify. So what I would like to do is, I will just come to this one. So we're going to jump directly to the actual demo part of it. If you want to follow along, I have already shared the actual GitHub link. I'm sorry, I think here there is a mistake. For CellStrat, I have created another one GitHub link, and you can directly take that GitHub link from here. So I will probably share you the link. I've shared it to Vishal and the team. Just try refreshing this. Okay, yeah. So I will just share this link in the chat window. And what you can do is, if you want to follow along, you can just follow along with me on the code that I'm going to execute. That's a link for your source code. All the code are available there. You can just download it. Let me just quickly go through the code, and then I will explain the details, because there is something that I need to explain. I need to initiate so that it can run. So I hope the actual this I'm using Google Colab. All the no setup is required. If you have a simple browser on your computer, you can still follow along if you have the Colab with you. So I will initiate the installation of the circ. So I think I have this working. Let me just quickly check. One second, guys. Yeah, my thing is connected. So I will just increase the font. And let me just start the installation. So it will take some time, like 2-3 minutes, for the installation to kick in and do. Let me just go to the presentation. By then it will complete the installation. Okay. Coming back here. So what are all the different types of qubits that we have? Basically, there are 3 types of qubits that you can define in circ. One is a named qubit, and next is line qubit, and the third is a grid qubit. The difference is nothing much of a difference, but named qubit, you provide a name, you can represent them. You can define multiple lines of a qubit, and grid represents, you have a different a grid of qubits that you want that you can actually execute it. Okay. From the circ perspective, it is not like, as I said, it is at a very initial stage of the development. Circ allows you to create any quantum circuits up to 30 qubits. You can execute up to 30 qubits. Beyond that is not allowed at this point in time, right? So let me just go back to my code, and yes, my installation is done. So the first thing is pip install circ. This will install the circ for you, and sometime it will ask you to restart your environment. I'm going to just restart the runtime, and once it restarted, I will be ready to go. So I'll give a couple of minutes. The first step is I import the circ. My import is done. So this is how you define the qubits. The first is a named qubit, and I'm defining Q0 as a qubit, Q1 as a qubit, and target as a qubit that I'm creating. This is how you create a named qubit. And line qubit, you represent how many number of qubits that you wanted to create, and it will automatically create the number of qubits that is there. And you can provide the range as well. If I say 3 and say Q1, Q2, Q3, that is also possible. In the case of grid qubit, represents the grid of the qubit that you want, 4 by 5. So you will have 4,5 grid that you will get as part of the qubits. Or you can create a square qubit that will create, for example, 0, 0 to 3, 3. I say square of 4, that will create all the qubits that is required, represented with from 0, 0 to 3, 3, something like that. So I execute this, and it has executed successfully. So the qubits were created. Don't worry, you have not able to see. So I was talking about Sycamore chip from Google. So Google also provides an option of accessing the qubit structure of the Sycamore chip. So if I execute this command, this will share. This is the structure of the qubits, how and what position the qubits were represented. That is what is represented here in this diagram that you get. I'm going to switch back to my presentation, and which is going to be, I'm going to be switching back and forth between presentation and the demo, so that you understand the theoretical part, and then you can do the practical parallelly there. Okay. So we talked about representation of the qubit, and we are starting with the practicals. Okay, the next important thing is circuit. Let's understand the basic premise of the circuit, and then we will see how do we actually define and create our own circuits for the quantum computers. The circuits as such consist of multiple parts. The whole part that you are seeing is the actual circuits. circuit. Now in this circuit, there are various small boxes that you're seeing. They are called operations. So this is what you see. There is an operation that happens. And each circuit has a specific moment, a specific moment at a specific point in time. That is what is the whole operation that happens on at a specific moment is called moments. And the qubits are the one which will be represented towards the beginning of your circuit. These are some of the items that you need to understand. And there is something called gate operation. So we talked about operation. The operations were also done by using something called gates. These are like AND gate or gates that you have learned. We are at that level from a quantum computing perspective. So we may have to define all this at this point in time so that your quantum computers can execute properly, right? So now you define the gate operation and take that operation to the next level. Okay. So let's see some examples here. So now the first example is, so there are 3 gates are being applied here. That 3 gates were performing some operation, and the result is equivalent to another gate that you see here. Okay. So now here there is something called H gate. The H gate is called Hadamard gate. So don't worry about if you don't understand what I'm saying it, but you will see them practically. So though you will understand it very clear. There is something called Hadamard gate. There is a Z gate, again Hadamard gate. So effectively the Hadamard gate is used for taking your qubit to a superposition level. Z gate is to actually rotate your qubit at the Z axis. And again, you are giving a Hadamard gate. You simply understand X gate is like, you move your actual qubit on X position. That is what you will achieve in the X gate when you apply. Okay, right. So some example gates. There are so many gates are available. Even there are people every day creating their own custom gates. It's all possible. C0 is C0 gate. C0 gate can be accessed by using circ.C0. The main purpose is to entangle 2 qubit. We talked about entanglement that can be achieved by using C0 gate. Hadamard gate that we talked about, you represent them by using circ.H. X gate, Y gate, Z gate, all these are there. The main purpose is rotate the qubit by X axis, Y axis, and Z axis. So that is the purpose. So you have detailed explanation of that as well available. And you can do some operations on the gates as well. For example, so I have an X gate that I have defined. I wanted to do a square root of it. You can directly utilize that. There are some gates even take some parameters. And for example, there is this Y power gate that you see. It can take a parameter of what is the exponent value, like 0.25 that you wanted to share it across. And before I go there, I will just quickly switch and show you how the gates are getting created. Okay, I switch to my code. I hope you are able to see. So we talked about the sycamore structure. Now the gates and the operations. Okay, we talked about first the actual qubit creation. Now we are talking about gates creation. We talked about circ.C0 is for your entanglement, and circ.Z gate, you can define your own variables as well for them. We talked about how you can actually do a square root of M, or Y power, which is going to take some parameters as well. Now, how do I combine the gate with the qubit that we define? So that is what we're going to see. Now here, I'm going to define a line qubit with a range of 2. That means Q0 and Q1 are the 2 qubits that I'm creating here. And once I create the qubit, I can apply, say, circ.Z on the Q0. That represents I'm applying this gate on the Q0 qubit. and I can say circ.c0 of q0 comma q1, that represent I'm applying the c0 gate on q0 q1, and then I apply a square root and the swapping operation on q0 q1. So this is an example operation. And similarly, if you have created some gates already, you can actually reuse them. For example, I created a variable for this particular circ.c0 as a c0 gate variable, and the same variable I can use here for my operation. So it is like how you create a custom variables, and this custom variable becomes kind of a data type that you have defined there. Those who are from the programming language background, they will understand this basics. Likewise, you can have your own gates that are being created, because the circ.z gate, I have given a name as polyz, and this poly gate can be directly used for your operations and so on and so forth. It's very simple. Let me execute this as well. So that execution has completed. You could ask, Prasanna, you're just showing me, I'm not seeing any output. Just bear with me 2 minutes, I'll show you. So gates we have created. Now comes the circuits. So, and the simulator. So the circuits, we talked about the circuits where I just show you the screen. So the circuits represents the qubits and your operations. The qubits, you know how to create qubits. The operations, you know how to create operations. The moments are something like what happens when you actually perform this operation. So that is what is represented by them, right? So now coming to the circuits, you have a circuit that is defined by circ.circuit, and there is an operation called circuit.append that will be enabled you to append different qubits that are there. Okay, so once I create the circuit, we talked about the steps in the quantum computing process. Is you have an algorithm, you convert that algorithm to a circuit, and that circuit has to be executed somewhere, then only you will get the output. The circuit can be executed either on a simulator, like similar to your mobile application development, or you can execute it on a real quantum computer. And by default, Circ provides a simulator, which is circ.simulator, that enables you to run your circuits. So that we will see shortly. Okay. So there are some advanced simulators were available, which are outside of your Circ as the actual framework. You can consider that these simulators are like custom simulators that were built for some specific problem areas and so on and so forth. And these simulators you can install and use them as well, part of your programming execution for your quantum computers. So one such simulator is called QSIM. So it is also Python based, and it can also help you on the simulation perspective. Okay. So, and it is effectively, before I go there, probably I've included that in the first this itself. Let me just go and we will purely talk about the practical part of it. Okay. So now, till now, what we did is we created the qubits. We understand how do we create the operations. Let's go to the circuits. So now I create a circuit using this. So once I create the circuit is going to have first thing as qubits. So the circuit, and I'm defining a qubit here with 2 qubits, q0 and q1. Okay, I executed it. Now, on these qubits, I can apply some operation and add this particular operation part of my circuit. So now here what I'm doing is I apply a Hadamard gate on a q0 qubit. That is the first operation that I'm doing. And there is a C0 operation I'm doing on the q0 and q1. And these two are two different operations that I wanted to add or append as part of my circuit. So that I'm appending here. So now you can, I can just execute this. Okay, the circuit is appended there. Okay, that represents I have added these two gates, and these two gates are going to perform some operation on the actual qubits. So now I need to see the results, right? So to see the results of this qubit, you have something called measure. The circ.measure will take the value of the qubits and provide you the results there. If I execute this, and that is going to tell, okay, fine, you have done some operation. After the operation, what is the value? Only using the measure, you can actually get the detail. Okay. So you will append it as part of the circuit. So it's a very simple circuit. If I want to see the circuit, I can just print this circuit. It will say 0 and 1 are the two qubits you are taking. They are line qubit. On the 0, I am applying on the H gate that is represented here. And on both 0 and 1, I'm applying the C0 that is represented like this. And once I done with this, I go for measuring it. The measuring is represented here, right? Okay. So we have created this circuit. So now we need to define the simulator. So that is what is done using this circ.simulators. So now the circ.simulators enable you to create and define a simulator. And once the simulator is created, you take the simulator and run the circuit on the simulator. Now what I'm doing is I'm running this particular circuit on the simulator and see what happens there. It is completed. Now I print the result of that particular simulator. Now here I represent 10 repetition I want. It is like similar to your epochs that you do in a machine learning process. So now what happens is, so this 10 times, 10 iterations that I'm doing on this whole detail. Okay. So now at the initial stage, forget about this 9 items. Okay. The initial stage, my Q0 was 0 and Q1 was 0. Okay. After the first iteration, it could be that the value of Q0 and Q1 has changed to 1, 1. And after that 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, like that, the actual execution has changed drastically, right? So this is from the simulators that we are seeing there. Okay. Now let's look at some of the other details that we looked at. So I need to understand what happens typically as a developer. You want to debug what is happening, how these particular steps are happening there. You want to see the steps, right? So we will see that shortly. So before that, what I wanted to do is, this is the actual circuit that you have created. I wanted to modify the circuit. I wanted to add some more operation in the circuit. So on this, let me take two different qubit. Now here I'm going to create a named qubit here. Okay. And in the same, similar to the previous execution, I'm going to do Hadamard gate on the first qubit and C0 on the other two qubits, that is 2 qubit, and measuring there. This is also another way of representing the details. And you could say it is the same, and you get that. And now if I want to see the moments in the circuits, how do I see the moments? Moments we talked about in the at any particular time, what happens in the circuit, that is what is represented by moment. There are 3 moments. There is 0, 1, and 2. The first step, the Hadamard gate is applied, and the second step, the C0 is applied, and the third moment, you get the measurement of it. There is another command called representation. This gives a JSON-based representation of your circuit's moments. So now here, when I click on represent this circuit 1, it is going to give me the details. There are different moments, and each moment represents what happens at that particular time frame there. Okay. So now we can apply the simulator, and we can apply the simulator, run that circuit, and print the result on the simulator. Okay. We have done. Let's look at modifying the circuit. Okay. I'm going to create another circuit with the same A and B as the qubits, but now along with Hadamard, I'm going to create an X gate. I'm going to put an X gate here, and do C0 and measure. So if I do that, so the circuit gets created, I create a simulator for it, I run it on a simulator and print the circuit. Now you can see print representation, and you can even add the details, like, you know, you can print the circuit as well. Print the circuit 2. Circuit as well. Now here you can see that you are applying for A, you are applying HMR, but for B you are applying X gate, and then you do kind of C0, and then you do the measurement. And now you can print the result of this particular gate. I'm sure that it will be much different from what you have got previously. Okay, so it is started with 0, 1, 0, 1, 0, something like that. But now here it is 1, 1, 0, 1, 1, 0, something like that. Okay, so now we talked about creating your circuit, how you can create your qubit, how you can create your operations using simple gates, how you can create the circuits, and how you can apply that into a simulator, and how you can actually get the output there. Okay, so we also talked about there are some specific simulators. These are external simulators, and these you can actually install as part of your programming. And these simulator will also help you actually come out with a simulation outcome. Okay, so now QSIM is one of the advanced one. I install it, I define it. Let's say I create a circuit with similar one, like H gate, X gate, and CX gate here I'm going to use, and then I'm going to measure Q0 and Q1. Okay, and creating a circuit. And once that circuit is created, I'm going to use both the simulators. Now here, apologize, yeah. So both the simulators. Now QSIM result, QSIM simulator, and that I'm printing what is the result of that simulator that I'm providing, and seeing what is the result there. And also I'm using a circ-based simulator. This is circ simulator. And for that, I'm running the same circuit on the circ simulator and printing the result there. Okay, both the simulators are there. So now this is the same gate operation. Now when I execute it on the circ simulator, I get this outcome, and I execute it on the QSIM result, I'm getting this outcome. Can anybody tell what could be the reason for this, from whatever that you understood? Hope I'm making sense, guys. What could be the reason? I mean, from whatever that the agility that we understood from the quantum computing perspective, what could be the reason that the circ simulator is giving something else for the same circuit, and the QSIM simulator is giving a different result? I mean, if you are wrong is also, that's fine, but just wanted to understand. Any thoughts? Okay, let me just give. See, effectively, we are talking about the qubit operations. The qubit operations as such, we talked about the superposition states, or the state on the actual sphere where you do not have control over where this particular point is. Now, because that point can be when the reading is happening, when the measurement is happening, the point could be anything. The influence of your alpha and beta and the get values can have an impact on where the position of your qubit is as such. And there are a lot of error corrections happens to measure it properly, and the advanced simulators does the error corrections in a much different way than a typical normal simulators there. So even though I introduced some of the gates, so these gates could represent and resemble some of the operations that a typical bit-based operations does, but you should also consider the error correction space as part of your actual execution as well. Okay. So I will just reiterate what we did in today's session is we looked at what is quantum computers, what are all the different frameworks which are available in the quantum computers perspective. We introduced you to what is a qubit, what is a ket notation, and why we are talking about the ket notation. And we talked about what is the difference between the way in which you interact with the quantum computers and the typical classical computers. And we have introduced the circ as the framework from Google, and we have created practically how you come out with your qubits, how you create your operations using some of the gates, and how you create a circuit, how you run that in a simulator as well. And effectively, to run the same circuit that you have created on the actual quantum computer, it is just one line of code, and the Google provides that line of code. What happens is, because it is basically scarce resource, the quantum computers are scarce resource. They do not allow you to create circuits which are more than 30 qubits, but you can utilize the real quantum computers to execute as well. They provide an API interface. Google provides in Python. You can just same circuit, instead of using a simulator, you just represent them and directly put it. But the difference is, because so many people might be utilizing it for their activities, there is a queue being created by Google, and using that queue, you basically execute it. So you may not be getting the response right away. So that's where I have not included on today's demo. I will certainly try to include it on the next demo that we plan to further continue our discussions on. Okay, now we're talking about introducing the circuits. Now, how do we take this conversation to a machine learning world? And what kind of an algorithms are available from the machine learning in terms of combining your classical machine learning algorithms with the quantum computer algorithms, so that, let's say, you wanted to do a neural network operations. So a part of your neural network operation, you can be using certain steps on the neural network operations, part of your typical classical computer way, your EDAs and your neural network definitions and so on and so forth. And probably at the time of execution, you wanted to utilize the capability of quantum computer so that you can execute it at a much faster pace. Because one of the problem that we see in terms of large language model creations, I'm sure most of you might have known about this GPT-3, GPT-2 and all these models are at a large scale language models. Like they work in billions and billions of data points and the features for their processing. One of the basic constraint is in terms of making your machine learning algorithm to work. Probably the Google would have taken multi months to actually process and come out with a model, because the capacity that we have currently are restricted when you run your machine learning neural network models for a large such feature space. In that case, you require a lot of processing powers to actually do that. But we are not at there in terms of utilizing your quantum computers for a complete neural network execution, but we are getting there in that space. So now it's almost 1 hour 15 minutes. I wanted to take 10-15 minutes for question and answer, and I wish to continue this session probably on the future date to help you understand the rest of the pieces on the machine learning parts. Now you understand the circuits, how you create a circuit for, say, a neural network based operation, and how you actually apply it along with a typical neural network flow that you do for specific problems. So that is the at the end. I've already covered them part of the slide. We are currently at around at the middle of the slides for our operations, but we still have long way to go in terms of achieving there. So let me stop and let me hear from you guys. Vishal, uh, over to you, please.
Okay, thanks for that. So, audience, any questions for Prasanna here? So, did audience, did we understand everything or we lost track somewhere?
Uh, yeah, Vivek, this is Shaila here.
Yes.
I don't have any questions, just I want to share my feedback. So
Hmm.
thank you, Prasanna. It was really very nice, very well covered on the topic on the quantum computing, the framework, the programming, and how it has to be used, and the basic executions, the basic libraries which has to be used. You gave a clear picture on how we have to start. If somebody has to start working on the quantum computing, so the basic knowledge which was very much needed, I can say you have provided that. A very nice foundation, and thank you for that, and waiting to see more sessions from you. Thank you.
Thank
Thanks,
you.
Shiva.
Thank you.
Nice comment for you, Prasanna.
Thank you.
So, Prasanna, there are questions on the chat.
Yeah, I apologize, guys. I did not see the chat. So, so some of the points I think I have covered. So, I think Mr. Gunjan has asked about, are we considering the volume of the sphere or just the surface of four values? So it is not the volume that we are considering or such, but effectively considered in a sphere. We have a point in a sphere, and if you need to calculate in which position that particular point is there, with reference to your ground state and the excited state. So consider one end of your sphere is considered as a ground state, another end is considered as a excited state, and within that sphere you put a point inside. And if you wanted to understand where that particular point is, what is represented as a qubit position, it is similar to how you toss coining. So just to help you understand, only I was explaining, when you toss your coin on the air, when that particular coin is running, and you need to know what is the value of that particular coin, which is a very interesting problem, because it can be zero, it can be one, or it can be both. That is the premise with which the quantum computers work. So it is both is what is the premise with which the quantum qubits work. And so if it is both, what is the value I should take? So it is a probability value. It can be near to zero, it can be near to one. So what probability value that I take? So that with that value, I will proceed with my calculation. So if that value is near to zero, I could be considering my quantum computer could consider that as zero, or if it is near to my one, then it could consider that as one as well. So that is a tricky part of it. So that is where the error correction comes. To simplify how effectively we are able to define the thing so that it correctly represents which is the nearby value. So that is what the actual error correction part that we're talking about, Mr. Gunjan. I hope I clarified this. And isn't Ket vector against a classical bit representation? No, actually, yes, Ket vector represents when you talk about 0 and 1. 0 Ket represents equivalent of a 0 in a in a quantum qubits, and 1 represents the vector representation of 1. But our interest is not 0 and 1. Our interest is when a particular qubit is in the vector space, it can be in any of the particular vector space. And what is the value? How do you measure that? That is where the formula that I mentioned there, that formula will represent to identify the vector space that qubit is going to be there. So that is what. Okay. Uh, Probability can be different. There is a question in the chat. Sorry. Yeah, I just saw. Okay. Okay. So the Ket vector against a classical, okay, is at the bottom of qubit computing. Still, there is a classical bit computing. Yes and no. From a programming perspective, you need a classical computer to interact with, but typical quantum computer does not require a classical computers. Okay. Algo developers' responsibility to convert algorithms into circuit. That's a very good question. At this point in time, that is how it is happening, and or there could be a different person who is actually working on algorithms, or there could be a programmer who takes care of converting that algorithm to a circuit. Yes, both are possible. Gates like math functions adapted for qubit computer. You are absolutely correct. The circuits are like representation, but gates are predominantly the math functions. Behind each and every gate, there is head spinning amount of math is behind it. Okay, so each and every gate has that kind of a math behind it. Okay, even I don't know any of those as well, so to be frank. Okay, so representation probably can be different. Ipshita, I'm not sure I understand your question. If you can ask, that would help. Articles, video, books to learn more on the topic. Sure, I can very well share the details, Mr. Pratik, and explanation of the infinitely intensive topic of research. Great initiative to the newcomers. Thank you very much, Mr. Sandeep. Very informative in the quantum computing. Beginners on subject. I found basic concept well covered. Thank you very much. Yeah. So because without this basics, if I start talking about putting a neural network and I'm going to create a circuit, then you will leave in 5 minutes. So that is how I see. So I need to give the basics so that you understand and you can enjoy the end-to-end picture of it. Okay. So interest in the math, just Google quantum computing by Parthasarathi. Okay. Sure. Sure. So even I never know. Okay. Good. Thanks for sharing it, Mr. Aditya. Any other questions, team? So I have shared my LinkedIn profile as well. I would encourage you guys to actually just connect with me as well, where I will share it again. And basically, it helps on continuing our conversation as well, if you guys want to. Okay, sure. This is a great session. Thanks for your hard work. Thank you, Mr. Aditya. Is anyone interested in the math? Okay. So, Mr. Vishal, Vivek, so I'm good. So, anything else that you want, we can talk
Okay,
about.
thanks, Prasanna. Very intense and detailed session on basics.
Sure.
I did try to follow through, but yes, I did get lost personally in the code a little bit. I need to spend some time on the code again myself to get a X confidence on that. But
Sure.
I theoretically superposition disentanglement I have seen before, so understood that. The getting logic in the code for me, I have to review it myself.
Sure.
But audience enjoyed it, and I do see some academic faculty as well from BMS or RV College.
Wonderful.
And just for information, I am a visiting faculty both at RV Department of Computer Science and also at BMS Information Science and Engineering. So
Sure.
we do collaborate with these colleges. So if anybody is interested from these colleges to be part of our AI research collaboration group, do reach out to CellStrat. And thanks once again, Prasanna. Look forward to your next sessions on quantum computing. Thank you,
Absolutely.
audience, for joining.
Thank you very much. And Ipshita has mentioned that yes, you are absolutely correct because of the probability only that the output varies from different simulators. You are absolutely correct. Right. Yeah. So thank you very much, team.
Thank you all.